In this video, we're going to look at how we can use the arc length of a curve as a parameter, which will help us understand the geometry of the curve independent of the motion along that curve. We've seen that different parameterizations can trace the same curve. Arc length gives us a way to construct a purely geometric parameter. When we use arc length as our parameter, motion along the curve occurs at constant speed. So if we look at the magnitude of the vector dr ds, in other words, the derivative of our curve with respect to its parameter arc length, that magnitude is always going to equal 1. We've seen the formula for arc length of a curve over a given interval. We can also construct an arc length function so that if r of t is some smooth curve, the arc length function s of t is going to be defined as the integral from a to t, where t is a variable, of the absolute value of r prime of u with respect to u. This relationship between s and t is going to allow us to turn any parameterization of our curve into a parameterization that depends on our arc length. Reiterating again why this idea of arc length is important, we know that the speed that we move along a curve can vary given the parameters that we've chosen. The geometry of a curve, however, should not depend on speed. Arc length is the thing that allows us to remove this dependence. In order to reparameterize a curve in terms of its arc length instead of some arbitrary parameter t, we're going to go through several steps. First, we'll start with r of t and we'll compute its derivative. We'll then find the magnitude of that derivative, which allows us to come up with our arc length function s of t. Once we establish that relationship between s and the existing parameter t, we can solve for t as a function of s, and then we can then substitute that back into our original curve. We'll know we've done this process correctly when we examine the new parameterization and we look at the derivative of r with respect to s. When we do that, the magnitude of that quantity should always be equal to 1. In other words, when r is written as a function of its arc length, its velocity vector is a unit vector with magnitude 1. Let's take a look at an example. Here we have the curve r of t equals cosine t sine t. And we want to determine if the curve already uses arc length as a parameter, and if not, we want to parameterize it in terms of its arc length. So to determine if the curve uses arc length as a parameter, what we're asking ourselves is, what is the magnitude of dr ds? If that is 1, then we can stop. If it's not 1, then we have to reparameterize. So this should be dr dt, not dr ds, because we don't have a t in there yet. So we're looking at, does this equal 1? So r prime of t is going to be the vector negative sine t, cosine t. The magnitude of r prime of t is the square root of sine squared of t plus cosine squared of t, which we do know is 1. So this is already parameterized using arc length. All right, let's try another. Same idea. We're going to check to see if it's already parameterized using the arc length, and if not, we'll go ahead and reparameterize it. So here, r prime of t is going to be the square root of, r prime of t, nope, no square root yet, is the vector 3, 4. The magnitude of r prime of t is the square root of 9 plus 16, which is 5, which is not 1. So this is not parameterized in terms of r of t. So let's look now at our function s of t, which is the integral from will go from 0 to t of the magnitude of r prime of u du. So it's going to be the integral from 0 to t of 5 du, which is 5u, from 0 to t, which is 5t. So now we have this relationship that s is 5 times t, which means that t as a function of s is s over 5. So if we want to reparameterize this, we can write it as r of s is equal to 3s over 5, 4s over 5. Now let's check this one. Let's look at dr ds. dr ds is going to be 3/5, 4/5. The magnitude of that is the square root of 3/5 squared plus 4/5 squared, which is in fact 1. Let's do one last example now. This time we've got a curve that actually is in 3-dimensional space instead of 2-dimensional space. So let's look at its derivative. The derivative of this curve is the vector function 2t, 4t, 8t. The magnitude of that is going to be the square root of 4t squared plus 16t squared plus 64t squared, which is the square root of 84t squared, which simplifies to 2 square roots of 21 times t. We'll assume here for our purposes that t is a positive number, so we don't have to deal with the absolute value of t when we take the square root of t squared. All right, well, that is not 1. So this is clearly not parameterized in terms of its arc length. So now we're going to look at s of t, and we'll look at this function, the integral from 0 to t of the absolute value of r prime of t, which we already know is 2 root 21t. Well, we're going to write that in terms of u, so we have a dummy variable inside of there, so our limit variable and our inside variable don't match. So that is going to give us 2 root 21 times u squared over 2, and obviously the 2's cancel. We'll evaluate that from 0 to t, and we see that we get root 21 t squared as our s of t. So now we know this relationship that s is the square root of 21 times t squared, which means in particular that t squared is s over the square root of 21. We don't need to solve that for t because if you look back at our original function, each of the terms has t squared in it. We can replace that with s over the square root of 21. So that means that when we rewrite r, we can write it as r of s is going to be the new curve s over the square root of 21, 2s over the square root of 21, and 4s over the square root of 21. I will leave it to you to convince yourself that the magnitude of the derivative of that new curve is in fact 1. So we see then that when we reparameterize our curve in terms of its arc length, equal changes in the arc length or equal changes in our parameter s are going to give us equal distances on our curve. This means that motion along the curve has unit speed. The velocity is always 1. We're going to look at the idea of the unit tangent vector and something called curvature, and we'll see that these reparameterizations simplify the formulas for those notions.